very much looking forward to the start of the first session. Aydin Keser, and he is presenting. So there's a difference in the program on your presentation. I guess you changed the topic.
I don't think so.
Oh no, okay, because here it says New Horizons in Analog Gravity. Ah, no, this is the meeting. Okay, good. The title is on the top. Sorry about that.
Okay.
So the title, okay, the title of the is Analog Stochastic Gravity in Strongly Interacting Bose-Einstein Condensates. Just a quick warning before we start. I will take all the questions at the end. So Aydin will have 20 minutes, and then we have 5 minutes for questions. Aydin, please start.
Hello, everyone. This is Aydin Keser. Today I'm going to present you the work that I've done as part of my PhD that I completed in 2017 in the University of Maryland with Viktor Galitsky. And after finishing the PhD, I moved to Australia. Currently, I'm in Sydney. And by the way, I thank the organizers for giving me the opportunity to talk as the first speaker, as it's getting pretty late over here anyways. So before starting, I would like to express my condolences for the late Parentani. And a very small anecdote, although I don't know him personally, his paper, Hawking Radiation in Bose-Einstein Condensates, was the first paper that got me started in Analog Gravity. At that time, I was in Melbourne visiting Monash University, and then because the US embassy denied my visa and put me through administrative processing, I was basically staying in a hostel and going to Melbourne Library every day, and all I did was to read Parentani's paper. And it's a very well-written paper, and the first author is Florent Michel. I'd like to thank him too. I think he's among us now for writing a very readable paper, which taught me a lot. Okay, after this, I'd like to start. And so there were a bunch of different motivations that propelled us into this study. And first was some resurgence of hydrodynamics in recent years. And briefly, hydrodynamics is basically a study of a many particle system at length scales that are larger than the scale where you can actually like resolve the components of the system. So in an electron system, the interparticle mean free path should be much smaller than your operating length scale, so that the hydrodynamic description is justified. In local thermodynamic equilibrium, you can write conservation laws for density and energy and so forth. And these are basically the hydrodynamic equations of motion. And recently, it's been applied to electron systems in graphene and also ultra pure heterostructures. And it was already applied to different systems such as superconductors, superfluids, Bose-Einstein condensates, etc. So fluid description in physics is pretty common and right now technologically relevant too. The second motivation was a topic that was favorite among us in our research group with Viktor Galitsky, and by that time there was also Justin and Hilary Hurst and Dmitry Efimkin with us, and Ian Spielman also wrote papers with them doing the experimental side. So this was about stochastic effects in Bose-Einstein condensates or superfluids. So briefly, if you have a quantum system, then Ehrenfest's theorem says that the averages behave like classical. And when the quantum system is living in a bath of oscillators, that is basically a heat bath, the quantum system decoheres, and then it starts moving like a classical object that's in a damped environment. And this damping forces and also the noise due to the heat bath are related to each other. And this statement is known as the fluctuation dissipation theorem. So I was wondering if I could generalize this to hydrodynamic variables rather than a single point particle. And the third was another another focus of activity in University of Maryland, basically led by Hu and his collaborators. And okay, this slide is about Analogue gravity, sorry. So the other part of the motivation came from Analogue gravity, where a lot of people, most of them are currently with us, and we are familiar with the people who started the effort. A lot of people realized that you can engineer a system to behave like gravity in the real sense. So one simple way to do it is to consider a perfect fluid. And when you consider the excitations on top of the fluid, the excitations look like they are moving inside a curved space-time. So what happens is, if you take the Lagrangian of a irrotational perfect fluid and expand it to find first-order excitations such as phonons, you realize that the phonon actually is a null ray in a geometry defined by this distance. And you can simply reformulate things by using a metric for this geometry. And the metric assumes the form of the ADM metric. And the Lagrangian for the phonon can be cast in this very compelling form, which is covariant. And then, of course, the equation of motion for the wave is the covariant wave equation. And this observation basically led to the fact that if you look at this metric G mu nu, at the point where c, the speed of sound, is equal to local speed of the fluid, you get a killing horizon, and you basically can have something like a black hole. And then people realize that this horizon also emits radiation, as does the astrophysical horizon. And finally, yes, this was what I just started talking about. Hu and collaborators wanted to go beyond completely classical gravity and consider what happens when you consider quantum fluctuations of the matter fields. And this is actually very much like how we treat the simple Ehrenfest theorem. So they said, just like you have classical equations of motion popping out if you take quantum averages, actually Einstein's equation, which is G is equal to T, is the semi-classical equation where the expectation value of T is the classical stress tensor, and the operator T itself is the quantum stress tensor operator. And they went further on, just like from semi-classics, you can go to noise in noise for a particle in a heat bath environment. They considered maybe the heat bath is the quantum fields, and then the particle is the space-time. So basically the matter fields create some noise and also dissipation on which the metric can move and change. And in turn, of course, the expectation value of stress is calculated on this dynamic metric. So combining all these motivations, I thought maybe we can write down stochastic equations of motion for a fluid and also the phonons living on this fluid. So let's see how we did that. This is a Venn diagram where all these concepts coincide. So we have Bose condensation and general relativity, and already in the intersection there's this analog gravity and on-rock metric, and we also put open quantum system paradigm into it and get a stochastic analog gravity system. Okay, our treatment should work very well in a strongly interacting system. The reason is in a strongly interacting system, you can write down this Gross-Pitaevsky type of Lagrangian as a perfect fluid, and the quantum pressure term is basically very small, and the smallness of this parameter depends on how strongly interacting the system is. So the stronger the system, the better the hydrodynamic approximation is. Of course, in a weakly interacting Bose-Einstein condensate, instead of phonons and hydrodynamics, you quickly get Bogoliubov quasi-particles and some effective mass. But in a strongly interacting superfluid, you basically have a phonon dispersion up to relatively high energies where the covariance breaks down. And this is our analog Lorentz scale. And it looks like this is feasible in actual superfluids because this Lorentz cutoff energy is much higher than the critical temperature of the superfluid. Once you have the superfluid and the phonons on top of it, then you can use this background field formalism and basically integrate out phonons and get quantum corrections up to 1, 2, whatever loop you want. And in this one, I'll use one loop corrections. Because as you go higher in this loop diagrams, the contributions become smaller and smaller. This is something very similar to quantum electrodynamics, where the higher loops decay with the fine structure constant and its powers. So on the superfluid, what we picture is the perfect fluid system, and the phonons on top give rise to the quantum field. So at the end of the day, you have the superfluid on the left side of the equations of motion, which obeys basically the conservation laws that are the mass conservation and the Bernoulli equation, the momentum conservation. And the phonons act like sources into these equations. So on the right-hand side, you see the stress energy tensor of covariant phonons. They are covariant because basically they are waves that travel at speed of sound. That is the analog of speed of light. And these covariant phonons create the stress energy tensor, and this tensor couples to the background fluid and creates the back reaction effect. It turns out that these superfluid plus phonon formalism, although it looks kind of unfamiliar, this is our analog to the semi-classical gravity and the conservation of stress, the covariant conservation of stress is also present in our case, simply due to the fact that energy and momentum are conserved. And the stress tensor of our massless scalar, which are phonons, are given in this form, and you can see the energy pretty simply as the 1, 1, 0, 0 component of stress. And of course, since we are doing quantum corrections, we have to consider the quantum stress operator, which is a more complicated object and is typically divergent due to the 0-point fluctuations of the fields, but there are a bunch of techniques to get rid of this and renormalize this stress operator averages. And one classical book that explains all this is by Brel and Davies, Quantum Field in Curved Space. Also, it looks like this renormalization plays a role in the stabilization of actual droplets. So I've cited this paper here, which describes how a liquid droplet is stabilized thanks to the energy of 0-point energy of the quantum fields. And in a completely flat case, which corresponds to a stationary fluid, our stress tensor average when renormalized, comes out to be this photon stress tensor. And there are nice proposals in the literature, such as by Balbino, Fagnocchi, and Fabri and Procopio, in which they consider the Birel and Davies renormalization and conformally flat cases to calculate the stress tensor. I mentioned that energy and momentum is conserved in our case, and in actual gravity, there's this covariant conservation law, which actually is not a total conservation law because the matter field can exchange momentum and energy with the background. However, by doing some manipulations, okay, this is a bit of a busy slide, but I'll just talk about it. If you do the total conservation, like the Noether conserved currents, you can prove that the total background stress and phonon stress are conserved. Well, which brings us to another subject, actually. By just following this line of thought of covariant conservation of momentum and energy and treating the superfluid and phonon system in semi-classical terms, we can basically rediscover the two-fluid Landau and Khalatnikov theory for superfluids. It turns out that these rather unfamiliar equations that are seen on the left-hand side, left top side, that is Bernoulli equation and conservation of mass, can be recast into the Landau-Khalatnikov theory, where the density is conserved and the superfluid velocity is described and the momentum is conserved and energy is conserved. That was very surprising. That was a nice, okay, it's not a complete surprise, but at least kind of convinced me that we are on the right track. Okay, since we've already described the semi-classical limit of superfluid and its excitations in a covariant form that looks like Einstein's equation, at least one part of it. And now we can try to look for how the fluctuations factor into this. And for this, I used the Keldysh formalism and basically tried to follow the steps of Hu and collaborators to see how I can get the fluctuation tensor into the equations of motion. So when you do the Keldysh formalism, you realize that in a physical system, there are two types of deformations. One deformation is virtual. So in D'Alembert's time, like in 18th century, people discovered classical mechanics by using these virtual deformations. So there is actually no real deformation of the system, but you imagine various deformations in the configuration space and find that the system obeys a trajectory that minimizes a quantity under these deformations. And Keldysh formalism basically says that this deformation is the quantum part. It's the quantum part of this like duplicated closed contour. And the real displacement, a real deformation, is the classical part of it. If you really displace an object, of course, you get friction and all sorts of things. So it kind of gives a mathematical justification for noise and dissipation in a dynamic quantum system. And when you do this Keldysh effective action on our superfluid system, you find that there's an effective action for phonons. And these deformations of the phonon field, sorry, deformations of the metric coupled to various tensors that arise from the effective action. So by analyzing the time reversal properties of this, you can see which tensors cause dissipation and which are.
Aydin, excuse me, you have 1 minute left.
Okay. So from these kernels, you can write down, okay, you can write down the equations of motion as you see with noises on the right-hand side. And these noises are related to the correlators of the stress tensor. And basically, what we got is correspondence between space-time and analog, space-time Einstein equation with noise and stochastic fluid dynamics. And also, we can prove the fluctuation dissipation theorem that relates the noise and dissipation tensors. And one interesting physical implication would be the aberration of sound waves due to the background fluctuations of the metric, but I didn't have time to really understand this so far. And I also obtained the Navier-Stokes equations and the viscosity of this formalism. And at the end of the day, I can say we've developed a bunch of theoretical tools to describe a superfluid and phonon system with its stochastic fluctuations in an analog gravity way. And I will be interested to see how we can apply this to various systems in different dimensions or setups. Thank you very much.
Thank you very much. We're now taking questions. I have a first question from Zach. Zach, you have to unmute yourself to answer to ask the question.
Yeah, no problem. Sorry, I thought other people would ask questions before me, so I didn't write this down yet. But at the very end, you said that you can actually sort of derive a Navier-Stokes equation with all of this. But I was under the impression that this was just for irrotational fluids, more or less in viscid fluids. Where does the viscosity term come from? That it
okay,
comes from tensor analysis that you're doing at the end.
Well, if you take the two-fluid theory and then try to get rid of phonons altogether, the second fluid, you can reduce the system basically to variations of the superfluid and what it experiences as internal friction. So it is not like Navier-Stokes equation as in a classical fluid, but Navier-Stokes equation of a superfluid that experiences internal friction due to the phonons and rotons and all that is excited in it.
So it comes from phonons interacting with other modes in the system?
It comes from, so by the way, if you consider a simple superfluid system that does not go into internal acceleration, this dissipation or this viscosity will be zero, and that is basically the premise of the Landau two-fluid system. So the normal fluid and the background fluid has zero viscous friction between them. But if you accelerate the fluid, like putting it through a Laval nozzle or putting it through a 90-degree bend or something like that, an effective description would be getting rid of the phonons altogether and describing a complete viscous system.
Neat, thank you.
Sure.
Any other questions? Okay. Jacopo?
Yes, so thanks a lot for the great talk. I have a curiosity about this formalism, And at some point you flashed the reference to a recent work about quantum droplets and supersolids by Lorian Chomaz et al. So what I was wondering is if your formalism could be used to describe those kind of system where the quantum fluctuations really stabilize some complicated many-body state, like quantum droplet.
Okay, that's a very good question. So in deriving this, what I basically did was to discard the divergent contributions. And I basically said that I move the divergent contribution from the right-hand side, which is the quantum fields, to the left-hand side, which is the pressure of the background fluid. And because pressure is a measurable quantity, and it basically stems out from interactions of the system, and we can basically hide this divergent term in the pressure term. Well, so this is what I did in arriving to these equations, but I don't know whether in an actual system you can get the full details of the interacting part, the pressure part, simply by renormalizing the stress tensor. I don't know the answer to that question, but I flashed that reference because it shows that the divergent contribution can't be hidden in the pressure term. I don't know if that answers your question, but that's all I can say.
More curiosity. Thanks a lot.